Swayam Prabha. Digital India. Educated India.
Jnanam Paramam Dheyam. Knowledge is supreme.
We are going to continue the proof of Jacobian criterion, and for this proof I will recommend you to see a book by Balwant Singh. The title of the book is Basic Commutative Algebra. It's by World Scientific. There it is proved much more general than what I am doing, but it's there in every. So the basic problem is once you set up correct notation and correct definition, things will become clearer. So I will go little slowly today. So last time I was trying to prove a lemma, let us recall that, and we have not finished the proof yet. So the lemma 1 which I will need for the main proof of Jacobian criterion. So that K is a field and we are working in a polynomial ring K x1 to xn, and this I will denote by capital A, and we have a prime ideal P here. P is a prime ideal in A of height m, height of P is m. Therefore, by our dimension arguments, we know that a dimension of A by P, this is equal to a dimension of, so n minus height of P, because height plus dimension equal to the dimension of the ring. So this is n minus m, and let us put this number as K. So that also shows that if I take the transcendence degree of the quotient field of A by P over K, so transcendent degree of quotient field of A by P over K, this is the dimension. So this is K. That means if I call this L to be the quotient field of A by P, this has transcendent degree K over L. L over K, transcendent degree is K. Okay, that means, so I can also assume, so first let me write the statement, then we will, so this is the situation. Then what do I want to do? I want to prove two statements. A, that I want to find m elements f1 to fm in P such that if I go to localization AP, in AP the ideal PAP is generated by this f1 to fm. This happens in the ring A localized at P. That is the first part, and second part B, I want to prove that if this L over K is separable, then if I look at the partial derivatives of Fi's with respect to Xj's and read mod P. So, this mod P Now this is, think of this as a matrix. This matrix has the numbers, rows are numbered by I, columns are numbered by j. So row numbers are m. So this is m cross n matrix. What are the entries? Entries are in, so this is in m cross n of A by P. So this is a matrix, you can see this is a matrix in L with entries in L. So rank of this matrix, that is the statement, the rank of this matrix dfi by dxj mod m mod p, this is precisely m, that is under the assumption it is separable. And let us recall separable. One way to think separability is there exists a transcendent basis so that the algebraic part is separable. So that is the definition of separable. Arbitrary field extension is called separable if there exists a transcendent basis so that the algebraic part of this is separable extension. And separable algebraic means every polynomial, the minimal polynomial of every element is separable polynomial, and separable polynomial means it has distinct zeros, no repeated zero, no multiple zeros. That is the, okay. So proof, we are proving, first we want to choose f1 to fm so that locally they generate p. Okay. So first of all we may assume, so I am denoting the A by P, this is small letters now, k small x1 to xn, it is a quotient of the polynomial ring, so it is the small letters this, and then our, this is the quotient field of this is L, L is the quotient field, so this is the quotient field. This is Q A by P, and there is K here. Okay, and now this is, therefore this L over K is generated by this small xi. So this L is capital K round bracket x1 to xn, because it is a quotient field of this integral domain. Now this is, therefore this x1 to xn I can choose. So choose, we may assume first the transcendent degree is k, that we know. So first x1 to xk is a transcendent basis of L over k. This we can assume because any generating set of a field extension will contain a transcendent basis. It is like a vector space, every generating set of a vector space contains a basis. So same, every generating set of a field extension will contain a transcendent basis. So I will renumber them and assume that x1 to xn is a transcendent basis of k, L over k. Alright. So again let me draw a diagram. So A by P is here, L is here, this is k x1 to xn, and there is a L naught here which is k small x1 to xk. This part is algebraic now, and this part is the transcendental part. So that is the situation now. This is a quotient field of A by P. And now I claimed last time something, and one of the trouble was it was the notation etc. was a little bit clumsier. So I have to improve that. Okay, so what is the claim? So take any integer L between 0 and m. remember that k plus m is n. So, take any L in between 0 and m, and then I have defined a map from L naught and then the polynomials, variables. So, which variables? Already L naught, these x1, small x1 to xk, already they are algebraically independent. So, they are also like variables. So, I take the next ones. So, that is x k plus 1, x k plus L. I cannot take more than m because otherwise it goes. So, look at this polynomial ring, and from this polynomial ring to L, I am defining a map phi L. So, I just have to assign where do the variables go. So, take any xith variable and map it to small xi. And I want to describe the image and kernel of this algebra homomorphism. That is what that will also lead us to how to choose the polynomials f1 to fm, so that p is locally generated by f1 to fm. Okay, so the claim is the following. There are three parts in the claim. Claim is image of EL, is the field generated by k x1 to xk plus L. So, this field I want to denote by L suffix L. That is the one part. What is the kernel? Kernel of phi L is generated by the polynomials f1 to fl, where these fi's are actually fi's belong to polynomials up to ith variable k, not ith, k plus I, x1 to x k plus I, and they also belong to P, intersection P. These are two parts, and the third part is under the assumption if L over L naught is separable. So, this is same thing saying L over K is separable. This is the algebraic part of that L over K. So, if that is separable given, then if I take the partial derivative of Fi with respect to the last x dx k plus I, this cannot belong to P. So, that is the claim. Claim is very simple, and if you do one by one, I am going to prove claim by induction on L. So, proof of the claim. This is by induction on L. So, remember L is that if L is 0, there is nothing to prove. Because what do you want to prove? Well, let us see here what you have to prove. If L is 0, you want to prove that the image is L0. L0 is the transcendental part, and then P is 0 and so on. So, it is nothing to prove. Okay, so we may assume L is bigger than 0, and already we have found the polynomial up to L minus 1. Already we have obtained F1 to Fl minus 1 with the property that we wanted, image of phi L. This one, kernel of phi L is generated by F1 to Fl, and they are all in P. So, already we have found this. Now, I want to do the next step, and next step is what now? I want to choose one more polynomial. So, just look at the element x k plus L. This is an element in L, and this one is algebraic over L0. And remember, we already have this L suffix L minus 1, which is by definition it was the image of phi L minus 1. This is image of phi L minus 1. Remember, phi L minus 1 is a map from the polynomial ring L over L0 from k plus 1 up to k plus L minus 1 inside L. So, this already found. So, this contains L0. So, already if this is algebraic, therefore, this is algebraic. Therefore, this xk plus L will have a minimal polynomial over L suffix L minus 1. So, xk plus 1 is algebraic over L suffix L minus 1. So, it will satisfy a minimal polynomial, irreducible polynomial. So, that I am going to denote by G. So, G is by definition irreducible polynomial of, so sometimes one denotes like this IRR x k plus L, not 1, this is L, k plus L over L suffix L minus 1. So, this is a polynomial in one variable over this field. So, this belongs to L minus 1, and the variable we are writing it capital X k plus L. So, the G evaluated at small x k plus 1 L is 0, and any other polynomial which when you plug it in small x k plus L, it becomes 0, then G divides that. That is the property of the irreducible polynomial. Okay. So, this is a polynomial over L suffix L minus 1, and this is the image of this phi L map. So, therefore, this polynomial G will definitely look like some polynomial Fl, and then it is a polynomial over over L suffix L minus 1. That means it has this x k plus L minus 1 and the variable. So, x k plus L, and it will be also. So, it is a polynomial over this. So, this one is a field generated by x1 to xk plus L minus 1. So, the divided will be h, common denominator will be x1 to xk. So, this is how G will look like, where because this h is in the denominator, the polynomial h x1 to xk, this polynomial cannot be in P, because everything is happening in L. L is the quotient field of A by P, where P is, so therefore, the denominator cannot be 0. So, therefore, that means the polynomial h will not be in P, ideal P. So, therefore, all these when you the numerator f, fl, this is actually polynomial in k x1 to xk, this is L, k plus L intersection P. This is what we have, because when I put xk plus 1 L here, it becomes 0. So, therefore, it is in P. Everything is happening in the quotient field of A by P, remember that. So, okay. Now, if so, what do we want to prove? We want to prove two things now mainly. We want to prove that this FL what we found here along with F1 to FL minus 1 and FL, they generate P locally at P. That was one, and second was the derivative of Fi by differentiation with respect to xk plus I, this cannot be in P. This is also we have to prove. Okay. All right. So, now if you assume it is separable, if you assume separating transcendence base, first I am proving derivative cannot be 0, but that was under the assumption that separable extension, right. I want to first prove this, the last part of the claim. So, for that we have assumption it is separable extension. So, because if L over L naught is separable, then LL over L minus 1, this is also separable, because these are in between fields. Okay, that means that the irreducible polynomial of any element here over this, the derivative of that will not be 0, the root will not be repeated. So, that will mean that if I take the differentiation of g dg with respect to this one dxk plus L and evaluate at where it is 0, that is xk plus L, this is not 0, because the g is a irreducible polynomial of xk plus L over this field L suffix L minus 1. So, but what does this mean? This means that, so that this means that if I differentiate, see if when you differentiate this and it is, so this means that df L by dx k plus L, this one is not in P. If suppose somebody is in P, that means you have to put all these small xi's and it should become 0, but it does not become 0, that means it is not in P. See, remember we are working in the field L, where L is the quotient field of A by P. So, if you want to test somebody is in P or not, you have to say it is 0 in L, but it is not 0 in L, therefore it is not in P. Okay. So, that first of all shows that, so first note that is FL, this already belongs to kernel of Phi L. This is clear, because how do I test somebody is in the kernel of Phi L? I have to replace all the variables by small xi's, but when I put the only one variable here is this. When I put this is equal to xk plus small xk plus L, that is like putting g xk plus L, and g this k plus L, xk plus L is the root of g, therefore that is 0, therefore these belong to this, is clear. All right. So, this shows first of all that if I take the ideal generated by F1 to FL, that is contained in that is, see I want to prove this is equal to kernel of Phi L. This is what we want to prove equality here. This is the first part of the claim, right. We want to choose polynomials f1 to fl, so that ideal generated by that is the kernel. That was the claim, the first claim here, this kernel of L equal to this with fi in this. So, fi's are already we have tested, now we want to prove the equality here. But equality also we have already proved this inclusion by induction, all these guys are in the earlier one, so later. So, this is already clear, only we have to prove the other way. So, to prove the other way I will take f here and prove that f is a combination of this, alright. So, f here means what? F here means if I put variable to be the small x size, it becomes 0. So, that means and we are only up to k plus L. So, if I put the last earlier variable small x size and the last one which is small x k plus L, that means this polynomial x k x1 to x k plus L minus 1 comma x k plus L, this is 0 means if I just look at this, that means G will divide this polynomial. So, that will mean that G divides f first k plus L minus 1 variable to small x size and the last one is capital. This divides where the division is in L minus 1 x k plus L. So, that means, so this divide this, that means that now just write down what does it mean. That means, so that means there exist polynomials R is in k x1 to x k plus L and S, H should come in the denominator. So, H should be not in P. So, it is in x k x1 to x k minus P, such that if I plug it in the first k plus L minus 1 variable to the small x size, I will get equation like this, f of x1 small x1 to small x k plus L minus 1 x k plus L times h x1 to x k. Remember, this h is coming from that g when we wrote g as a rational function. Fine. So, this divided by FL x1 to x k plus L minus 1 comma x k plus L, this is equal to R x1 to x k plus L minus 1 x k plus L divided by S x1 to x k. This divide this, so write this f is a multiple of the g, and multiple means, so this g was written as, I will show you, g was written as this. So, I just cross multiplied it. So, just cross multiplying it, we get this. Now, this equality means what? You cross multiply it. So, cross multiplying, what do you get? You will get like this. So, now cross multiplying it, this S times F times H. So, I will write H S F, this is S times this F times this H equal to R times this FL. So, this is equal to R times FL. and we are interested in the coefficient of as a polynomial in the variable x k plus L. So, first of all, this belongs to the as a it belongs to the kernel of FL, kernel of phi L minus 1, because you just this is think of these are polynomials k plus L and compare the coefficients. The coefficients, when you do this equality, coefficients are equal. So, the other side is, so that shows that this polynomial is actually in the kernel of FL minus 1, and kernel of FL minus 1 is generated by the polynomials F1 to earlier polynomials F1 to FL minus 1. And now look at this H and S, they are not in P. So, therefore, when I localize it, it will go down there in, I can go down in the denominator. So, therefore, this F will belong to the ideal generated by F1 to FL minus 1 and along with this FL locally, that is clear because H and S they are not in P. So, that implies F belongs to ideal generated by F1 to FL minus 1, and this ideal is now in not in A, but A localized at P, in the ring A localized at P. So, that proves that what we wanted to prove, we wanted to prove that the kernel, so that proved the equality here, you see, that proved the equality here because we took arbitrary F here and we proved this F is in ideal generated by this locally. Okay, so that proves this this claim. Now, in the claim I am going to use it for the last guy, that is L equal to M. So, that means what we have proved is kernel of phi M is generated by F1 to Fm, and this was in actually the field K x1 to xk and then the polynomials after that. This was it, but this is contained in A localized at P. So, therefore, when I localize it, you get locally, so locally they are correct. So, now, so what is the statement we want to prove? The next statement that that the rank of the matrix is M.